Hi, the section 5.5, the zero-inflated count models. So some count variables have the excessive zeros compared to Poisson distribution. So for example, the number of arrests for individuals is mostly zero for most people, but still a few people are arrested many times. So if we exclude the group with the zeros, then the variable has the wide variability, but we have many zeros. So this cannot be expressed by just Poisson distribution. So the zero-inflated count models add one more parameter to count models to represent the inflated probability of y is equal to 0. So one more parameter in addition to the count models. So we studied the two basically the same models. The one is the huddle model and the other is mixture model to account for the inflated probability of y is equal to 0. So first one, the huddle model. So huddle model means that we have some huddle to have the positive y. So we have basically the two stage. So at first stage is the whether or not the y is 0. And if y is not 0, then we fit the count model, for example, the Poisson model here. So probability of y is equal to 0 is just estimated by the f1 of 0. So this is just one number, but it depends on the predictor variables. And the probability of y is equal to j for j is equal to 1, 2, 3, and so on is defined by 1 minus f1 0 over 1 minus f2 0 times the f2 of j. So this sounds complicated, but this coefficient just makes the total probability equal to 1. So think about the summation of probability of y is equal to j. Then we have this factor a times the summation of, okay, so f2 of 1, f2 of 3, and so on. And this is equal to 1 minus the f2 of 0, because we assume that later we assume that f2 have some probability distribution. So the summation of f2 is equal to 1. So the f2 of 1 to f2 of 2 and up to f2 of infinity. So that is the 1 minus f2 of 0. So this part cancels with this one, and the summation of the probability of yj from j is equal to 1 to infinity is equal to 1 minus f1 0. So then we can add up these numbers, f1 0 and 1 minus f1 0 to get 1. So the total probability is 1. So f1 0 is estimated separately, and f2j is estimated by the Poisson distribution. And here the probability of the y is equal to 1. So this is the huddle part. Huddle part is estimated by a logistic regression because this is just one probability. And f2 is estimated by Poisson regression. So the model combines basically the two components. One is logistic component, and the other is the Poisson or another count model component. And the other model is mixture model. So this is essentially the same, but the probability of y is equal to 0 is defined as the phi plus 1 minus phi times f of 0. And the probability of y is equal to j for positive integers is defined by 1 minus phi times fj. So this is kind of simpler in the sense that this part is in common. So if we take the summation over all j, 0 to infinity of this f of j, then this becomes 1 because we assume this f of j is Poisson distribution. So the total is actually the 1 minus phi because the both part have the 1 minus phi as the factor. So to And if we add this phi, total probability becomes 1. So essentially, this is the same as the previous slide because the basically the probability of y is equal to 0 is considered separately. Then after that, we use just one Poisson regression model. So here's interpretation of the huddle and the mixture models. And the huddle model estimates the probability for a positive count. So that's why we say this is a huddle model. So we have a huddle to have positive y. And the mixture model, on the other hand, estimates the probability that an observation is in the group that always y is equal to 0. So remember that this term, we have two terms for y is equal to 0. And the first group, this probability, with this probability phi, the individuals never have positive y. For example, the number of the chess games played today. And some people never play chess, so that is always 0. But some people sometimes play chess, but just by chance on that day that they didn't play any game. So that part is represented by 1 minus phi of f0. So in this sense, the mixture model estimates the probability that an observation is in the group that always y is equal to 0. So this is phi. So slightly interpretations are different. And okay, so essentially these two models are the same, but since parameterization is very complicated, it's highly nonlinear parameterization for logistic part and also the Poisson part. So the estimation results slightly differ between these two models. And which model to choose? Usually the results are very close. So interpretation that may be the more important. So interpretation of this probability or this probability, so that determines which model to use. Yeah, so this is the theory for the zero-inflated count models.